Okay, that's good. So, first of all, thank you very much to brum.ai for giving me an opportunity to present my work in front of such a good audience. So, thanks a lot. And today I'll be talking about my research that I'm working upon, and my presentation is about discovering trade-offs in fairness and accuracy in machine learning systems, a multi-objective approach. And this is what we'll be discussing in my presentation. First, we'll discuss what fairness means in AI with the help of real world examples. Then, how can we analyze fairness in machine learning systems, the mitigation strategies, the multi objective optimization approach that we use for our problem, then the results and future research questions for to further go in my research. So, in recent years, there has been a shift from focusing exclusively on the accuracy of machine learning systems to a more holistic and human centered approach that includes privacy, fairness, transparency, and more. And claims regarding the biased nature of AI is not speculative. There is substantial evidence indicating the existence of bias in these systems due to factors such as race, color, ethnicity, or religion. So, some of the examples of algorithmic bias in real world are Amazon recruitment algorithm. So this algorithm is basically used for recruitment algorithm for segregation between whether a person is fit for the job application or not. So in 2015, the algorithm was found to be biased against female applicants because the algorithm was trained on a decade ago data set where they had more male applicants, say resumes, and that is why whenever a female applicant used to give the application, it used to get rejected because the algorithm used to put penalties on it, and eventually used to get rejected. Similarly, the Compass algorithm, which is being used for recidivism check for in the U.S. courtrooms, and it was biased against the Black Americans, and then the U.S. healthcare algorithm, which is biased against Black Americans. So. So from these examples, we understand that algorithmic bias or fairness issue exists in machine learning systems. Now, how can we mitigate this bias in artificial intelligence? There are many ways, like having better governance, like having better guidelines, like the EU guidelines, which was published in 2019, and many more such guidelines. And the second way is to have better data sets, and the third is to identify and analyze the bias and then mitigate it. And that is where our lab is interested in doing the research to identify the bias, analyze it, and then in the later stage mitigate that bias from machine learning systems. So now, if I summarize my research, what we do is we first explore the relationship between accuracy and different notions of fairness using a well-established case study based on a public credit scoring dataset, where training a model using standard techniques has shown to lead to bias predictions. So once we analyze the bias and we get to understand that bias is there, the next step is to explore the trade-offs between accuracy and the different fairness metrics using multi-objective training approach, which aims to maximize both the objectives, that is accuracy and fairness. And what our research tries to do is just train the algorithm in such a way that the biased nature which persists in data can be mitigated, and by introducing evolutionary algorithms in our problem, we are able to achieve it to a greater extent. And this is the paper from where I started my research a year and a half ago. And this paper was published in 2018 by Sahil Verma and Julia Rubin, which talks about 20 different notions of fairness. And they divide these 20 definitions into three broad categories: the statistical models, similarity based models, and causal reasonings. So if we see, statistical models can be proved through probabilities and confusion matrix, but similarity based models and causal reasonings are more intuitive definitions. Like if we take fairness through unawareness, this definition takes no sensitive attribute during the decision making process, but this can introduce bias somehow through the proxy variables. So for our research, what we have done is we have concentrated on the statistical models, and among these statistical models, we have concentrated on these six definitions of fairness, that is for group fairness, predictive parity, predictive equality, equal opportunity, overall accuracy, and treatment equality. I'll just give an overview for the intuition behind these definition, how these definition work, and then we can move forward. So group fairness basically is, checks whether the positive predictions in the data set is equal among the different demographic groups. For R, the demographic group was male and female, because sex is the sensitive attribute. So the intuition behind this definition is that after the algorithm is trained and the predictions are being generated, positive predictions should be consistent across different subgroups in the data set. Then predictive parity not only considers algorithms predictions but also compare them with the actual outcome of the data set. And the intuition behind this definition is that the probability of a subject with positive prediction value should truly belong to the positive class. Then predictive equality calculates those instances when the model's prediction is positive but the actual outcome is negative. And a society may face serious repercussions for having high false positive rate in the predictions. Then in equal opportunity, if we invert the notations of predictive equality by swapping the predictions of model from positive to negative and the actual outcome from negative to positive, we can calculate the equal opportunity. And for overall accuracy, it evaluates the model's probability of correctly predicting positive outcomes when the actual outcome is positive, and the model's probability of correctly predicting negative outcomes when the actual outcome is negative. So overall accuracy can be crucial while conducting fairness analysis, particularly in the healthcare data set. And the last one, that is treatment equality. It calculates the ratio of false negative and false positive for different demographic groups in the data set. Now, once after that, we conduct a fairness analysis on the data set, and this is the overview of for our fairness analysis. So once we have the data set, we pre-process the data set and split into training and test set, and then generate the predictions. And once the predictions are being generated, we need 4 attributes for conducting the fairness analysis. The first one is the protected attribute. For our case, it's the female applicants. Then the unprotected attributes, that is the male applicants, then the predicted outcome and the actual outcome. And once we have these 4 attributes, with the help of confusion matrix, we can calculate we can do fairness analysis for all the 6 definitions and compare whether the difference is significant or not between the 2 subgroups or not. And this is the result for our baseline experiment. And so this table is basically summarizing for all 6 different definitions and the 2 subgroups, that is male and female. And prior to our research, practitioners used to use arbitrary threshold to choose whether the difference is significant or not in the subgroups. So if we choose an arbitrary threshold of 6%, then it would mean that if the difference between the subgroups, that is male and female, is less than 6%, then it can be said that the predictions are fair. But if if the difference between male and female applicants is more than 6%, then it would be then it says that the predictions are unfair. But this is really domain specific, because if we are looking at a healthcare data set, we would want that this arbitrary threshold should be as close as possible. But in a credit score data set, we would say, okay, 6% might be fine. So what we wanted to do is we wanted to change this and wanted to have a more uniform and general way for conducting these fairness analysis. And that is where we introduced the statistical test. We ran the algorithm for 30 different times with the random seeds, and then did the statistical test to check whether the difference between the 2 subgroups is significant or not. So if you look at the arbitrary threshold way, which was done prior to our research, so for predictive parity and overall accuracy, the threshold is less than 6%. So it says that that these definitions are fair, but all the other 4 definitions are unfair. But according to our by conducting the t-test, we found out that all the definitions are giving unfair predictions. So from here, what we understand is that as accuracy is increasing, there is fairness issue or bias issue in the model. So these 2 objectives are contradictory. Now, once we understand that this bias exists in the machine learning model, the next step is to mitigate that bias in the machine learning system. And this is the mechanism for employing fairness in machine learning systems. The first way is to do pre-processing step, where we modify the data before training the algorithm, or we can do the in-training process where we modify the algorithm that is trained, or at the end, the post-processing one, where we modify the predictions of the model. And what our approach is, we are using the in-training process where we are introducing the multi-objective optimization problem for training the algorithm in such a way that we can have maximum fairness and maximum accuracy at the same time. So moving forward, I'll just give a brief introduction of what multi-objective optimization problem means, and then what we have implemented in our research. So a multi-objective optimization problem tries to optimize more than one objective function simultaneously in any given problem. And these objectives are usually conflicting, making it challenging to satisfy all of them at the same time. So let us take a real world example to understand how multi-objective optimization works. So consider someone is traveling from Toronto to London, and we need to book a flight ticket, and flights are available at prices ranging from few thousand to a couple of 100,000. And if we consider the two extreme hypothetical cases, one ticket would cost around $2,000, which would be in an economy class, and the other extreme case would be for $5,000, which would be in a business class. And if we consider only cost as the objective function, then optimal solution involves choosing an economy class ticket because we are saving money. But with this, the airlines would no longer be needing a business class ticket. And however, for our example, the objective is not only price, but it is comfort as well. And buying an economy class ticket would result in compromising the comfort. But if we look at the executive customers, comfort might be the prime objective, and solution two might be the optimal solution. And this leads to the two objective optimization problem. And between these two extreme solution exists many more solution where we can find the trade-off between cost and comfort. So it means that by compromising a little bit in cost and comfort, we might find a premium economy. And this is basically according to the need and the budget of a person, and the decision can be made. So these trade-offs formulate a front known as Pareto optimal front in the objective space. So now coming back to our problem, what our problem is, what do we require? We have two objectives that are conflicting. We understood it from the analysis. Now what we need is we want fairness and accuracy to have maximum fairness and maximum accuracy at the same time, and that is what we want. But that is not we can always get. So there's sometimes we might get a trade-off, or sometimes we might not get a trade-off, having maximum accuracy and maximum fairness, and that is what we want to achieve. And this is the overview for our multi-objective approach. So we have the input data, we initialize the weights and the bias, and then use evolutionary algorithm. And then after that, once the predictions are being made, we need 4 attributes for conducting the fairness analysis. The unprotected group, the protected attribute, the predictions and the actual outcome. And once we do the fairness analysis, we have the second objective as accuracy. We can calculate that accuracy as well. And once we have these two objectives, we wrap the whole process in a multi-objective optimization framework known as PIMO, which helps us to understand the trade-offs between fairness and accuracy. And we can understand whether we are able to achieve maximum accuracy and maximum fairness at the same time or not. So this table summarizes our multi-objective results, comparing them with the baseline results from single objective training across all fairness notions, the 6 fairness notion. And when we implement fairness analysis on standard machine learning models and conducted the statistical test on experiments, the result shows that these techniques led to biased predictions. But by incorporating a multi-objective approach in the in-training process, apart from predictive parity, which suggests a trade-off between accuracy and fairness, all the other 5 definitions satisfy both our objectives, suggesting a fair and accurate model. This shows that by employing fairness in multi-objective approach, when a trade-off was assumed, the results the results that we got show that there is no trade-off between two conflicting objectives satisfying a problem which was missing in the single objective approach. So this is the video which I recorded for just showing how between the two objectives in the objective space, the trade-offs can be formulated. So this has been done by running for the algorithm for 10,000 generations. So if there is a trade-off, if there is a trade-off between the two objectives, we can see that as accuracy increases, there is the fairness difference between the two subgroups increases. But if there is no trade-off, we'll find that as accuracy increases, the fairness difference is low. So from this, we can understand that as the accuracy increasing, there is no trade-off, and both the objectives are being satisfied. And these are the future research questions that we would like to look upon. Now we want to validate with different data sets. And once that is done, if a data set contains multiple sensitive attributes, how can we choose most important sensitive attribute for the fairness analysis? And the third one is to optimize among various fairness dimensions that may present conflicting priorities. So between these fairness definitions, these fairness definitions are conflicting with each other, which satisfies our multi-objective optimization problem. So by working between the two fairness dimensions, we can understand whether there is a trade-off or whether we don't get any trade-off. So that is where we are looking to go ahead. Thank you very much.
You just missed the applause. It was a loud applause. Okay. Would you like to thank you for the presentation? This was super interesting. Can you hear us?
Yeah, sure.
Okay, let's try this. So I'll see if there are any questions, and then we'll just take it a little bit slowly. Any questions? Okay, just one question.
Hi. First, I wanted to say thank you very much.
Oh,
sorry,
yeah.
Can you hear me?
Too slowly. Yeah. Yes.
Oh, yeah. Thank you very much for the amazing talk. Just was wondering, is this something that's more applicable with models that have yet to be trained or you're in the process of training versus a model that's already been trained and you know to be biased? Because I know in a lot of cases you spend a lot of time and effort in training up a model, you know, hundreds of thousands of pounds sometimes in compute resources. Is it something that can be fixed on the fly, or is it something that you really need to do from the ground up to get it truly fair?
Thank you.
I'm not able to hear the question properly. Can you just repeat the question? There's some disturbance.
So you're able to hear me on this?
Yeah, better.
Oh, awesome. Yeah, so I'll cut the question short, but effectively, is it easier to make a fairer model as you're training it versus a model that you already know to be trained in a way that's biased, just because like a lot of these models cost a lot of computational resources and are sometimes quite expensive to train? Is it something that can be fixed after the fact, or is it something that you really need to think about before training a model?
So you're saying that we can the model that is being trained in such a way is computationally less. Can you just repeat? I'm sorry.
Sorry. Effectively, when you train a model, it's quite expensive to do so.
Yeah.
From like a money perspective, a time perspective.
Yeah.
If you train up a model and you realize that it's biased once you've spent £100,000 training it,
Yeah.
are you able to fix after the fact, or is it something
Yeah,
that you
after
really
the fact. Yeah.
have to begin with?
Once it is being analyzed, once it is being trained, the predictions are out. We analyze it, and once it is being analyzed, because we are doing the in-training process, and that is why we are once the predictions are out. After that, only we are using the in-training process to mitigate that bias.
Awesome. Thank you very much.
Okay.
That was a great question. One more question.
Hello, can you hear me?
Yeah.
Thank you. It's a great talk, by the way. I was just curious about the multi-objective optimization policy. Is this as simple as just adding a term to the objective function that's a penalty for fairness and another term for accuracy? Or is it more complicated than that?
It's not that complicated. I guess it's the first one to just put in between the two objectives.
Okay, thank you very much.
Hi, thank you. I was curious because you spoke about different kinds of bias. So you looked at the sex example, but also spoke a bit about race. Have you looked at what kinds of bias in terms of like those metrics you mentioned in the circle? Are there specific types of bias that are more prone to showing certain metrics, or is it largely the same no matter what kind of demographic you're looking at?
So right now in our research, we looked upon the individual bias that is between if there is sex between male and female. But the next step, what we want to do is to go further and do upon group bias. That means that between different groups, if we are looking at race and sex, it will be group between the finding the group bias, and that is where I guess. Your question would be like we haven't done it yet in that domain.
Okay, interesting. Thank you.
Final question. Sorry. Yes, perfect. Thank you, Arsh. This is the final question.
Yeah.
Sure. So my question might be more philosophical, but who decides what's fair versus the accuracy point of view? So there, as you mentioned before, there are many, many different groups that you might be considering. If you, the observer, are looking for a bias between two particular groups, how do you know that you're training the model to be fair versus ignoring another group variation, say social economic background, for example, that you might inadvertently be training the model to be biased towards?
I think you're talking about the proxy variables which can affect the biasness in the model even after if we are doing it on specific sensitive attribute, if I'm not wrong.
Yeah, exactly. In your earlier use cases, you described, for example, the racial biases that have been observed in the court judicial systems. You've observed the gender biases within the Amazon recruitment.
Yeah.
By tweaking the models to look for those particular biases, how do you know that as an observer, you're not influencing the results against another bias that you haven't maybe yet observed or trained yourself to look out for?
I don't know because I haven't thought of yet in that direction.
Sure. I guess it's a who watches the Watchmen kind of question, but a tricky one.
Question. Okay. Thank you, Ash. Thank you very, very much. That was a super interesting talk, and good luck with the next steps. Hope we stay in touch.
Sure.
Bye.